systems. Dr. Ibrahim is a professor of nuclear medicine at Cairo University, and he's on leave now to Riyadh. So we missed him in Egypt. And I would like to give your kind attention that in case you have any question, please write, and we'll discuss all the questions by the end of the lecture. And now I give the talk to Dr. Ibrahim. Further, Dr. Ibrahim.
Thank you, Professor Gaber, for your kind introduction. I'm honored today to have Professor Gaber Ziada as a moderator for this session. Professor Gaber is my mentor and my supervisor during my entire career, actually. I was honored to be chosen also by Professor Hosna Mustafa, a great name and a pioneer of nuclear medicine in Egypt and in the Middle East, and also the president of the Egyptian Society of Nuclear Medicine Specialists. Is the voice clear for everyone?
Yes, it is.
Yes.
Okay.
Yes, Dr. Ibrahim.
I want also to extend my thanks and appreciations to the Egyptian Society of Nuclear Medicine Specialists, especially Dr. Ashama Hani and Dr. Maya Amr, to coordinate for such scientific events, which will help all young nuclear medicine physicians in their career. Actually, our today's session will be on the physics and technology of SPECT systems. In this session, we will explore how photons are transformed into diagnostic images using gamma camera technology. Our objectives for today's session are to understand the main components of the gamma camera, review the principle of operations, and discuss how these principles evolved from the original Anger camera design. To have an overview about the modes of acquisition used while using the gamma camera, also to concentrate on the SPECT acquisition and have a quick review or overview about the SPECT processing. Okay, sometimes I ask myself, how can we see radiation? Of course not, we can't see radiation of photons. So this question was answered by several scientists in the earlier ages, and we can see the effect of radiation actually in every device that we are using in everyday life in nuclear medicine and the radiation field. So the effect of radiation actually can be biological, chemical, or physical. One of those, so if we look for chemical, for example, we can detect radiation by OSL or TLD. So chemical exchange happened because of radiation, and then we can measure it. So we can measure the radiation taken by the body, by any worker or the public. Also for the physical point of view, the effect of radiation as a physical quantity, we can use it in detection of radiation, like using it in gamma camera, because it changed the radiation is changed into a light emission. Then we can detect this light emission. Okay, so let's start by having a brief historical idea about the gamma camera. The story of the gamma camera begins actually in 1957 with Hal Unger, who developed the first scintillation camera. His design still used until now, until today, with some modifications from here and there. The device was capable of detecting gamma rays emitted from within the human body and translating them into spatial information. The Anger camera was revolutionary because it simultaneously captured 3 essential data points for each detected photon. The first one is the XY positioning. So we will know the position of the photon, where it comes from, the energy of the photon, and the exact time of detection. This combination allowed for the correlation of physiological processes in real time. And this is a photo of Hal Unger with his first gamma camera. The first commercially available camera was delivered in 1962 by a nuclear Chicago company to W. Myers at Ohio State University. That early version had only 7 photomultiplier tubes. Yet it introduced the essential concept of the current gamma camera, planar gamma camera until now. Okay, so modern gamma cameras have evolved to maximize both image quality and efficiency. There are 3 primary performance features we focus on. First one is high detection rate, and then the scatter rejection and high sensitivity. A high detection rate ensures that the system can process thousands of gamma events per second without data loss. Scatter rejection improves the spatial accuracy by filtering out those photons that have changed direction within the body. Finally, sensitivity determines how effectively the system detects gamma photons, influencing image quality and acquisition time. Okay, let's start by having this famous photo of the composition of the gamma camera. We find it in every book and the physics of nuclear medicine for Simon Cherry. Here we will start the journey, but briefly we will discuss it now. The photos comes from the patient. I'll use a pointer. The photons comes from the patient and goes directly to the collimator, which is the first layer that will interact with it. It will not interact, it will actually filter it. So the photons in appropriate direction will go through the holes of the collimator and goes to the crystal. The crystal is sodium iodide crystal doped with the thallium. In most of the cameras, actually, now we have new ones. And then in the crystal, the photon transformed into flashes of light or scintillations, we can call it. And these scintillations are transformed into electrons in the photocathode of the photomultiplier tubes, which is arranged symmetrically on the crystal. The photomultiplier tube magnifies this electron into a significant detected signal, which is then passed through several circuits. We will go for them one by one in the next few slides. Okay, we will start our journey of the gamma rays emitted from the patient by knowing about the collimator. Think of it as a camera's lens. The collimator is a thick piece of lead or tungsten, or a combination of lead and tungsten. Only those rays goes in straight or appropriate, because we have different configurations of the collimator, can go through the holes and reaches the crystal. Others will be absorbed within the septa, which is the spacing between all the lead between each hole. This makes the gamma camera throws most of the radiation, but it's absolutely necessary to create a clear image. So this is, for example, one of the collimator exchange system. I think this is for 40 gamma camera, Philips 40 gamma camera. It's one unique design. Okay, in this slide, we can classify the collimators in different ways, in many ways, actually. The first one is we can classify them according to the accepted energy. So we will have low energy, medium energy, high energy collimator. And this nomenclature is according to the energy accepted or used while using this collimator. So for low energy, we can use isotopes up to 200 keV. For medium energy, from 200 to 300 keV. And high energy is from 300 and above, up to 500 keV for most of the cameras. So for low energy, we can image technetium, medium energy gallium, high energy for iodine 131, and so on. Also, we can classify them by resolution. Resolution, we will have several vendors offer several nomenclature for the collimators according to their specification. So we can find low energy general purpose, low energy high resolution, ultra high resolution, and super high resolution. They have different collimator opening diameter, hole diameter, And so for that reason, they increase in the resolution from one to other. Also, the last one, or the first one actually, the classification by geometric shape. By geometric shape, we can have the parallel Hall collimator, bane Hall collimator, converging collimator, and diverging collimator. Under them, we have such other nomenclature for them, which is we will find in the next slide. Those are the classification of collimators according to their geometric shape. We can have at least 6 basic designs. The first one is parallel Hall, which is most common design, the converging, the diverging, and pinhole, slant hole, fan beam collimator. And those are the figures for each one of them. We will go for one by one for all of these collimators. So we'll start with the parallel Hall collimator, the most widely used design in clinical gamma cameras. All the holes are drilled parallel to each other, so the image appears exactly the same size. So we'll find the image here, which is I, the object is here, O, the arrow is pointing to the left, and here the arrow is pointing to the left, which means that the same size of the object will be imaged, no magnification, neither inversion. So the same direction of the object will be the same in the image. The magnification here, of course, will be 1 as m equal I over O, which is equals to 1. Let's move to the converging or focused collimator. Here, the holes are angled in front of angled inward, so they meet the focal point in front of the detector. This geometry produces magnified image of the objects positioned between the focal point and the detector, helpful for small structures such as brain and heart. We can express the magnification as m equals I over O, which is equals to F plus L over F minus Z. I know that all of you hate equations, but this is so simple. Whereas F is the focal distance. If we can see, F is here from the collimator face up to the focal point. Z is from the object to the collimator face, and L is the collimator thickness. And here is the I, as we have seen before, and O, I is the image, and O is the object. So M will be calculated, or magnification will be calculated from this equation. For objects between the collimator and the convergence point, the magnified image will be non-inverted. Beyond the conversion point, the magnified image will be inverted. So we should take care that we image patients below or closer to the collimator to, like we see here, the focal point typically from 40 to 50 centimeters off in front of the collimator. So we need to be as close as possible from the detector face. And this is, of course, for all imaging using the gamma camera. This is ABC. We should make the object or the patient as close as possible from the detector face. Okay, in contrast, the diverging collimator is essentially the reverse of the converging one. Its holes spread outward. So here is the position is inverted. If you see, the object is here, and here is the image. So the focal point is on the other side. Okay. This design increases the field of view, make it ideal for large organs and whole body scans. It's demagnification. Here we have demagnification, not a magnification, calculated by M equals F minus L over F plus Z. And we know before the identification of each letter. As the distance Z increases, the image becomes smaller because of the wider field coverage. Diverging collimator allow imaging of large anatomical areas without moving the detector too far from the patient. A valuable feature for general nuclear medicine, especially for obese patients. So it's very famous in US because they have a lot of obese patients. This is our favorite and old friend, because pinhole collimator was the first one to be used for thyroid scans. Now we can call it the pioneer for the collimators. It needs a lot of space, so we can't use it with dual head gamma cameras. It can be used only for for single head gamma camera, because of technically it's not applicable. It uses single small aperture, usually from 3 to 6 millimeters wide, made of dense material such as lead or tungsten, like every collimator we said before. The pinhole projecting an inverted and magnified image onto the detector. The magnification is described by M equal F over Z. So here, the arrow is pointing to the left. This is the image, and the object actually is pointing to the right. So if we are imaging the thyroid, we should take care that the left lobe will be inverted on the other side and the right lobe will be inverted on the left side. And this will be changed if we cross the focal point, actually the same like in the fan beam collimator. However, because magnification varies across the field, there can be a geometric distortion at the edges. So careful calibration and positioning are therefore required to maintain diagnostic accuracy. This is a very rare one. This is a very special type of collimator, which is the slant hole collimator, at which parallel septa are tilted at the same angle with respect to detection scintillation crystal. It is used mainly for breast and cardiac imaging, and I have never saw it in my career. Fan beam collimator, this was my favorite one, because this collimator I did my PhD thesis on a topic related to fan beam collimator in brain scan, perfusion scan. The fan beam collimator is a hybrid design combining both parallel and converging geometries. Along the head, from head to foot direction, the holes are parallel. So it's like parallel hole collimator. And from the lateral to the radial direction, in the radial direction, so in this direction, the holes are directed to a focal point. So the magnification, this design provides magnification in one plane while keeping parallel projection in the other plane, making it ideal for imaging organs like brain and heart, where depth, details, and resolution is very critical, of course, for brain and heart. Although the field of view is smaller than that of the parallel hole collimator, the improved count sensitivity and spatial resolution make fan beam systems valuable for high precision studies. Okay, let's summarize how the collimator directly affect the image quality. So it will affect for sure the image quality, which type we are using, what collimator we should use in a certain scan or certain type of scan. So we have four main parameters that can govern this process. The first one is the hole diameter, the hole length, the septal thickness of the septa, and the object distance. So from the object from the collimator face, how it affects the image. So we'll give a brief example. Smaller holes will give high resolutions actually, but lower sensitivity because it affects the number of photons that is coming to interact with the crystal. Longer hole also improves the resolution but decreases the sensitivity. Thicker septa for high energy, especially for high energy photon, to prevent septal penetration. So for thyroid, we can find the star shape. If you know, of course, all of you know, the star shape comes from the septal penetration of the photons with the high energy photons. So if we increase the thickness of the septa, it will prevent this penetration, and it reduces the resolution due to geometric spreading. These trade-offs are at the heart of the gamma camera optimization. So optimization is very, very hard word that we can use is to find the most suitable with the least expenses. That I can explain it in very, very frankly way. When designing or selecting a collimator, one must allow always balance resolution and sensitivity and acquisition time to fit for the clinical need. As acquisition time is very important, by the way, because the patient can't stay still for more than half an hour. So we need to adjust our needs according to the clinical case and also, of course, to the need of the patient. Here we have a table that explains different types of collimators from different vendors and their specification. So we have here the length of the hole diameter, the septal thickness, and in effect we will find the sensitivity and resolution. Well, let's take the first two as an examples. So for low energy high resolution and ultra high resolution, the length here is almost the same. The whole diameter is different because the high resolution is wider than the ultra high resolution. The septal thickness here is almost the same. It's not very big, but the sensitivity is completely vary. From low energy high resolution, it has a higher sensitivity than that of ultra high resolution, but on the other side, the resolution is inverted. So for ultra high resolution, we have better resolution as a system. So it is extrinsic, not intrinsic. So system resolution of 7 millimeter is very good. 8 millimeter is very good, but the ultra high resolution gives more resolution or more details for the image. Okay, now we have explored all the collimator types and we consider it as a lens and it filters the photons. So those photons who comes through the collimator will interact directly with our detector, which converts the radiation into light. And here is the concept behind this gamma camera is to detect the radiation by transforming it into light and then electrical signal for sure. So now we have explored all of this. We will move to the conversion of the gamma camera into visible light. The heart of the detector is the scintillation crystal, actually, because this is the most expensive part of the gamma camera, which is in almost all the gamma cameras is sodium iodide activated with thallium. Nowadays, we have new detectors, of course, coming. It was under research for several decades, and now it's available for all of us. It's very expensive, actually, but it's very, very different from the normal type of gamma cameras that is using sodium iodide crystal, which is the cadmium zinc telluride. We can find it in several vendors like GE, Siemens. There is a very, very new and good design. I saw it lately, which is the star shape. I don't remember actually. One of the GEs that's having a moving collimators, moving detectors, so it can make the contour. It can image the contour of the body without doing any hustle. So it's very, very new technique. Getting back to our traditional one, sodium iodide crystal is chosen because of its high atomic number and density, 3.6 gram per cubic centimeters, which give it excellent stopping power for the gamma photons. Typically, the crystal diameter is from 40 to 50 centimeters in diameter and from 6 to 12.5 millimeter thick. Previously, we call it 3/8 inch or 5/8 inch. 3/8 inch for the whole general nuclear medicine. 5/8 inch can be used for annihilation detection. It's large enough to cover most of the patient's field of view. It has two important physical parameters. The first one is it is brittle in nature, which means it can be broken easily. It is hygroscopic. Hygroscopic means it absorbs humidity, so it's very dangerous for it. So in most of the design, we will find an aluminum casing to hermetically seal the crystal, and on the other side, there is a glass which is the contact point between contact area between the crystal and the photomultiplier tubes. Okay, one of the specifications of the crystal is that the thicker the crystal, the more likely it will absorb the photon, of course. So it improves the sensitivity. But thicker crystals also degrade the spatial resolution because light spread before reaching the photomultiplier tube. So it spreads within the crystal before reaching the photomultiplier tube. So we will decrease the resolution. So there is also a trade-off: thicker crystal, higher detection efficiency, but poorer resolution. Thinner crystal gives us better spatial resolution, but reduced sensitivity, especially for high energy photons. Okay. If we have the flashes of light or the scintillation within the crystal, we need to change it into an electrical signal. So the first part that will interact with the flashes of light is very thin layer that is called photocathode. This photocathode will transform the light photon into electron, like you see here in the yellow area. So at this area, the light photon will be changed into one electron. This one electron will be magnified in the photomultiplier tube with a series of what we call diodes. These diodes are connected with different voltages, each one with different voltage. So it enhances the electron to be magnified, multiplied from one to other, and then come to at the end and gives us a readable voltage, which is a signal. So at this point, we have a signal, and then we will treat with this signal with some electrical circuits. In typical gamma cameras, the photomultiplier tubes are about from 2 to 3 centimeters in diameter, and they are arranged together in a hexagonal array. We can find different numbers from 61, 75, 91 BMTs according to the field of view of the gamma camera of the detector. It depends also on the detector size, like we said. Each tube responds differently depending on its distance from the light flash in the crystal. So to ensure they have identical gain, each photomultiplier tube should be calibrated before usage. So if one photomultiplier tube is lower, the region of the image will appears as dim area. If it fails completely, it will be like a circle with a cold circle. So it can be transformed by physicians to a misleading diagnosis. So both of those cases, becoming dim or becoming a cold area, is not acceptable for diagnostic images. We can, from this image, we can see how is the photons are detected by the photomultiplier, by the whole array of the photomultiplier tube. When light from the crystal reaches the photomultiplier array, each tube produces a signal. So for each one of those will produce a signal, depends on how close it is to the site of interaction. The gamma camera's electronics analyzes these outputs to determine the XY coordinates. This is the first thing, and representing the position of the event within the detector. Then Z pulse representing the total energy deposited in the crystal. The system uses a weighted sum calculation, which is, if you see here, we can find a number that is 424, and around this number we can find 78, 74, 74, 78, 82, 82. So all of those are around each other. So it's nearly the same number, around 80, but here it's too high. So as we go far from this photomultiplier, we can find that all of the counts or count statistics or signals for those photomultiplier are becoming degraded. So it's 3, 5, 9, 8, 11, and so on. So from this figure, we can be sure that this photomultiplier is the XY coordinate of the event that we are receiving from this photomultiplier tube. So this is the point of interaction or the point of detection from the patient. Okay. So now let's talk about the electronics that handles the photomultiplier out, specifically the pulse height analyzer, or BHA, we can call it BHA. This device ensures that only valid unscattered photons are included in the image. So the signal from the photomultiplier tubes first passes through the pre-amplifier and the main amplifier. So pre-amplifier, we will see their benefits on the next slide. And then into the multi-channel analyzer, also we will know about it now, which produces a pulse histogram. Pulse height histogram, it's like this one. This we can see in the energy window calibration. Every day in the morning, we need to calibrate for the energy window for technetium, for iodine, for gallium, for every isotope we are using. We need to make an energy calibration for the window. This histogram is produced actually by the multi-channel analyzer. Essentially, an energy spectrum showing the number of pulses at each energy level. Each gamma rays emitting isotopes has characteristic photon energies. For example, technetium, of course, have 140 keV, like we see here. So now let's look closer with what BHA spectrum tells us. The Z pulse represents the total energy of each detected photon. By plotting the Z pulse frequency versus energy, we get an energy spectrum. In an ideal system, you will see a clear photo peak representing full energy absorption event, allowing, we can find it along with smaller peaks or continuums due to scatter or secondary interactions. So for multi-energy, like gallium-67, we have different peaks, each of which has a different percentage or contribution to the histogram. We know that the most prominent one or dominant one is 93, which is 40%, 185, 20%, 300, 70%, and 393, 5%. So this multi-channel analyzer do its job in this situation. Okay, we said before that we have a pre-amplifier and amplifier after getting the signal from the photomultiplier tube. So actually pre-amplifier, it makes the signal suitable or what we can say adjustable or adjusted in order to be magnified. So here we adjust the signal if it is not like this shown on the picture. It will be like this one. So this is a complete signal that is shaped correctly. And then the amplifier will make it bigger. So it is detectable now. So this for the pre-amplifier and amplifier. Now we come to the pulse arithmetic circuits, or the circuit that is responsible for calculating the X, Y, and Z coordinates. This pulse arithmetic circuit is very important because any problem in this one will mislead us completely, and it will lead to different positioning of the photons coming from the patient. So this is very important. Also, one of the main circuits, which is a pulse timing circuit, and it manages the timing window and prevent pulse pile up. And I will stop at this pulse pile up effect. Pulse pile up effect means that we will, if the gamma camera receives a huge number of events at the same time, it will not accept it. It will not accept all of them at the same time. It will remove a lot of them. It will detect only maybe half or quarter of them. And this happens especially in high count rate studies, like first pass, cardiac first pass. For cardiac first pass, I know that it is not used commonly now, but it was one of the exams that have huge count rate. So this one is corrected or adjusted by the pulse timing circuit, and it prevents the camera to become paralyzable in high count rates. So now we will briefly discuss the types of events that gamma camera can accept or can happen during imaging with gamma camera. If we can see here, we have different types of photons coming from the patient. So the first one is A, which is coming from the patient directly run through the whole of the collimator and then detected by the crystal and then the photomultiplier and so on. The second one B will come from the patient directly to the holes of the collimator, but interacts with the scintillator, the crystal, and then moves away from that point of interaction. So it gives us two different events or detected flashes in the crystal, and it misleads us. For C, it actually scattered within the patient. So the origin of the photon was here, goes to the left, and then interact with another patient dense area or bones or something like that. So it interact with this one and goes for in a forward direction randomly and goes through the whole of the collimator and detected in the crystal and gives us an event that is not here. It was supposed to be in this area, not in this area. And for D, actually, it passes through the septa and it has been detected, but it is not in the same area that should be. So it should be in this area, not here. So all of these three, B, C, and D are not accepted for us. It will be scattered radiation and gives us the background that we see in most of the cases. But A is the only contributing photons that is really comes from the patient from the same positions that we need. I'm behind time, so I'll move quickly. Okay, this was the first part of our session today. We have gone through the gamma camera components one by one, and then we will go to the technology, which is the mode of acquisitions used in gamma camera. We have actually five modes of acquisitions: a static, dynamic, whole body or total body, SPECT, single photon emission computed tomography, and gated imaging. So we'll go for the first three of them. We know them very. Most of the new physicians have gone through several types of imaging using static imaging, dynamic imaging, and whole body imaging. So static imaging acquires a single image. The patient is fixed, the camera is fixed during a duration or count. So we can stop the image by after 5 minutes or after 500 kilocounts. We will use several metrics. We can use matrices starting from 32 up to 1024 by 1024. And typically it's used for static images like thyroid scan, spots for the bone scans, and so on. The dynamic image imaging is like a video. So this is what gets the gamma camera unique. It gives us the opportunity to see the function, like kidney function. So it captures the sequences of frame over time. So a frame, a static image, each, let's say, 5 seconds, 15 seconds, 20 seconds, as the exam protocol have been chosen. To observe the physiologic function, such as renal scans, like we said, showing tracer uptake and excretion. So this dynamic imaging is very famous, and it is unique for gamma camera. Now it's not unique. We have the other modalities are providing the dynamic imaging, but we was the first. Going to the whole body imaging, we in the earlier ages, if I can say, we used to image on a single head gamma camera static image only. We don't have whole body. So what happens is we spend 1.5 hours for imaging one bone scan. So a static image for each part of the body in the anterior and then in the posterior. Now we can do it in 10 minutes maximum or 7 minutes according to the protocol. So the whole body, actually, the camera moves from head to toe by a certain speed. This speed is determined according to the injected activity. So we can say we can move from 10 to 20 centimeters for bone scan, 10 to 20 centimeters per minute according to the injected activity, actually. And it can be used also for all whole body imaging like surveying or searching for a tumor or metastasis for bone scan or for gallium 67 or technetium maybe and so on. So these are the three basic ones that we know. Those 2D modes we have explained here form the foundation for tomographic imaging, which we call SPECT. So SPECT imaging, it's actually single photon emission computed tomography. So single photon to differentiate it from annihilation photon. So it can differentiate this type of imaging from the annihilation, which is PET, lately PET. And then it generates a cross-sectional images. So it is CT, and emission is because it is emitted, the photon emitted from the patient. So it's imaging from various angular projections. So if we get back to the dynamic image, it is static images, but at the same position of the patient, but with different timing. So it gives like a movie. Here we have several positions around the patient. So each static image will contribute to the projection. So projection from the whole circumference of the static images around the patient. So the gamma camera heads rotate around the patient, acquiring multiple planar projections from different angles. Then computer algorithm reconstruct these cross-sectional images, giving us tomographic slices of tracer distribution in 3D. So like we see here, it's moving around the patient from the dual head gamma camera, or we can also have it from triple head. This will be the result for the projection images. It's not a clear or clinical image, so before reconstruction. So let's consider this is the first static image we have, and then moves gradually with certain projection angle or angular projection until we finish all the projections around the circumference of the patient. After reconstruction, it will be like that. So this is the clinical image that all of the physicians will write their reports using it. Okay, the process of SPECT begins with acquiring a series of planar images, like we said, with a uniform angular increment. So the camera moves with a specific angle, not different angles. So 3 degrees, 6 degrees, and so on. Each detected event is assigned to the corresponding computer bin address, creating what we call a projection data. A full set of projections across 180 degrees or 360 degrees constitutes to the raw data of tomographic reconstruction. Each projection represents how the organ appears from the specific angle, and together they encode all the spatial information required to rebuild the 3D image. We will go for the imaging acquisition parameter one by one. So starting with the patient orientation, this is an easy one, but it is very essential to take care of, which is very important because it will change the orientation of the patient if we made it by mistake and change the orientation. So if the patient is head first, and we tell the camera that he is feet first, it will change the right to left orientation. So it will mislead the physician while writing his report. I believe this is a fatal mistake, and no one will accept to have this mistake. So it's very important. Going to the type of rotation. So we have different types of rotation. We have step and shoot and then continuous. Step and shoot, the camera stops at each angle. So this angle, and this moves to this angle, and so on around the patient. During the stop position, it will acquire image, it will acquire count, and during movement, it will not acquire count. So we have here about 4 seconds left without any acquiring of data. It will affect the final image. The other one is a continuous one. So the camera moves gradually, like the whole body, the camera moves gradually from head to toe. Here it will move gradually around the circumference of the patient with a very small speed. So it images the patient while moving. This will turn in what we call a blurring effect. So if we are going to, with our cameras or with our mobile phone, and we are going to have a shoot for a moving car, we will find it in the image, it's like a blurred image because it's moving. So it's the same concept here. So we have advantage and disadvantage for each of them. One is giving high resolution because it images the patient while it is in the zero movement. The other one is imaging all the circumference during movement. So all of the vendors have managed to get us the option of combination of step and shoot and continuous at the same time. So it is there. So it images at the stopping position and then images also while moving from one stop to the other stop. So it gives us an optimized solution for that problem. Going to the other one of the acquisition parameters, which is elliptical versus circular orbits. And for sure, now we have the auto contouring. So the elliptical one is to move in elliptical rotation or orbit. The circular one will move in a circular with a certain radius without any movement of the detector during the acquisition. So for the elliptical, it will be in this position and this position, and in the anterior stopping or anterior motion, it will come closer to the patient to give an elliptical one. Most of us are using the elliptical for most of the studies, but for brain, we can use the circular one. Now we have auto contouring, so the camera moves up and down, while moving around the patient. We teach the camera how to at several points before beginning of the scan. And other cameras also have auto contouring without any teaching mechanism. So it can move with a laser sensor. So it doesn't touch the patient at any area. Okay, the other imaging parameter is 100 degree and 360 degree. This rotation arc is depending on the position of the organ itself. So if the organ we are going to image is inside, in the center of the body, for sure we will use 360 degree. But if it is near to the surface of the body, like the heart, all of us are imaging heart with 180 degree from left and right anterior oblique to left posterior oblique position. And you can see here in this image that this is the image of 180 and this is the image of 360. We can't figure out which one is better from my point of view, but actually from the physician point of view, it's very important. But doing it with phantom, it will not be suitable because we don't have any attenuations from the other area, like we are imaging. Here we are imaging the cardiac, and we have from the other side, the spine, the whole lung. So the photons will scatter from different medias. So this will be not suitable for clinical usage. So 180 degree is enough, especially for heart and the lumbar spine. Lumbar spine also is in the back and it's near to the body surface. We can image it from from right to left, posterior, without having the anterior projections. The acquisition time is very important also because, as we said before, the patient can lie only for 30 minutes to 40 minutes. So the acquisition should be adjusted according to this time. So, for example, if we have intervals of 3 degrees interval with single head, so 50 to 80 seconds frame will be enough. But if we are going to use 6 interval, we will double the time because it should be double to be from 30 to 36 seconds, the double of this one. Moving to one of the important parameter, which is matrix size. As regard to the matrix size, actually it is the smallest element of the image. So the matrix is the smallest element of the image. So it's like one square of those squares. It can vary from 332 by 32 up to 1024 by 1024 squares. The matrices are defined by the number of subdivisions along the x and y axes. So if this is a detector, so we can count those squares on the vertical axis, and those squares on the horizontal axis, it will be the matrix size. So it's an easy process. So the greater the number of pixels, the smaller is each pixel for a given field of view. For the same field of view, if we see here, this is a bigger matrix. Bigger matrix. Here the language will affect it because here the matrix size is the number by a number. But the size of the matrix itself, the square itself, will be smaller for higher matrices. So this one is bigger square size. Here it is smaller, here it is very small. So the resolution is getting better when we decrease the pixel size, okay? So we have matrix size and pixel size, okay? Matrix size is the number by number. Pixel size is the square dimensions. Okay, during imaging with the gamma camera, the detector size is fixed, okay? So we need to have certain zoom type. Some of the technologists used to image the patient as it is without any magnification. But the situation here, if we use the zooming technique of the used in the gamma camera, we will concentrate on a certain area. So the matrix size will be concentrated on this area and gives us better resolution. And by the way, we can calculate the matrix size, the pixel size by this formula, which is the field size, the detector size, let's say 40 by 60 or 50 by 60, over the matrix size, which is 32 by 32 or 128 or 128, and so on. When applying zoom, the field size is divided by the zoom factor, which means that the resultant field size is smaller, and using the above equation will thus result in smaller pixel size in millimeters. And here is the final one, I think, which is the number of projections. The number of projections can vary from 6 degrees or 3 degrees. So 60 at 6 interval or 120 at 3 interval. Of course, we need to optimize the timing between both of them. And we can calculate the number of projections before going to, I'm running out of time. So this is an empirical formula that helps to determine the adequate sampling for the image. It can be calculated like this is the circumference of the patient, 2 by r, multiplied by 2.5 over the resolution. So if we need the resolution, let's say give an example for it. If we need a resolution of 0.9, so putting it in this equation, the circumference is 45 multiplied by 2.5 over 0.9 will give us 125. So we don't have 125, so we'll go for 120 images per 360 degrees. So this is a very fast example. Getting to the last part, which is the spectral construction. So we have now the images from various projections, and we need to reconstruct it. We have two different ways. The data acquisition, we'll start from the data acquisition, recording a set of angular projection. Each projection represents the intensity distribution of radiation along the given path. And then the image reconstruction is the creation of cross-sectional images from the projection data. The simplest way of them is the back projection. The computer takes the 2D images around the patient and smears it back across the image area. The problem is the founding of the star-like artifact and the blurry image because of the projections are simply added together from various projections. So this method is the simplest one used in the clinical daily usage. To fix this blur, we use a filtered back projection. So back projected and then filtering it. This is the most common and fastest method before the back projection step. So the computer applies filter like RAM filter to the raw data. This filter mathematically removes all the blurring component. We use different filters to control the balance between resolution and noise. RAM filter removes all this noise, and we also apply a roll of filter like Hamming, Hanning, Butterworth to smooth it, but so smooth it without noise. Choosing the right filter is very important in the clinical case, because we need, for each hospital, for each clinic, need to accept a certain protocol, what we are going to use as a filter for each type of case. So for cardiac, we use, let's say, Butterworth with a cutoff on the and so on. Hamming and Hanning for brain with a cutoff and so on. So we need to fix these parameters for the technologists, not to let them do everything by their choice. This is the ideal situation, actually. Here we can see the different projections are transformed into a movable projection. All projections for a single slice, we hear this nomenclature a lot, the sinogram. Sinogram is actually one slice. So if we consider these are a single slice for two objects, one large and one small, and we are moving around this object from 360 degrees. So it will be here in this position and here in this position and so on until the end. So this sinogram is very important in the beginning of the SPECT processing, because if we found a crack in any of these smooth line, it will give us an indication that there is a motion of the patient or there is a problem in the detector alignment. So there is no other option. This is very important before going further for reconstruction. The modern and superior method, of course, is the iterative reconstruction, such as OSEM, OSEM, or MELM. And instead of one step like a filtered back projection, iterative reconstruction is the process of guessing, refining. Firstly, the computer makes an initial guess, okay, of the image, calculate what the projection should look like, compares them with the actual data, and then make a correction for this guess. It repeats this process for several times according to our choice. At the end, we will find a very smooth, high-resolution image according to what we are going to use as an iterative technique. The advantage of the iterative reconstruction, it gives better image quality, less noise, and it's more accurate for other physical factors like attenuation and scatter. Previously, it used to take a lot of time because of the computer processing capabilities, but now it's very fast. It can be done in a second. And this is a figure for combining all the differences between filter back projection and iterative reconstruction. Nowadays, we have, of course, what we call whole body SPECT, and it can be found in from several vendors. Some gamma camera specific vendors like GE, Evolution, Philips Astonish, Siemens Flash 3D, and other universal softwares, BEX software like Hermes, Scavis, and UltraSPECT. The final one is the gated acquisition. It's actually gating means the image collection is synchronized with the patient's cardiac cycle. So usually we are using the ECG trigger at the R wave. The entire R wave interval, the entire RR interval is divided into discrete frames, which usually from 6 to 16, 8 to 16 or 16. Photons detected during the same portion of successive heartbeats. So for each one of those, detected several heartbeats, creating a series of images that represent different phases of the heartbeat. This technique lets us to observe the wall motion and the ventricular function in real time without blur. In get SPECT, the SPECT acquisition itself is linked to the ECG signal. Each projection is divided into the same number of frames as the cardiac cycle. So data from multiple heartbeats are accumulated frame by frame over 10 minutes or so, according to the protocol, providing statistically robust images for each phase. The system also includes a beat rejection window. So any beat that is not in the same harmony of the heart cycle, it will be rejected. Typically 20 to 30% variation of the RR interval to discard irregular beats and preserve imaging consistency. Once collected, the frame can be reconstructed into sine loop, displaying the heart in motion, or analyzed to quantify for wall motion and thickening, left ventricular ejection fraction, and also contributes to the polar map. And it gives us a perfusion defects within the myocardium. This integration of function and perfusion makes the gated SPECT one of the most clinically valuable tools in nuclear medicine or nuclear cardiology specifically. Clinically, gated SPECT is used to visualize regional wall motion, detecting hypokinesia, akinesia, dyskinesia, quantifying ejection fraction for therapy and monitoring, and assess perfusion defects like we said before. Here, a slide that gets all the gated SPECT in brief. And its clinical applications. In conclusion, the collimator defines the direction of the ray. So we start our journey by the collimator from its emission of the from the photon emission of the body through the collimation, detection, signal processing, and finally to image reconstruction in SPECT and in gated SPECT system. Understanding these principles help us to optimize clinical protocol and interpret images with confidence. Thank you for listening and also for your attention throughout this session. It was, alhamdulillah, I finished it in 1 hour. I hope this overview has enhanced your appreciation for physics behind modern nuclear medicine imaging. And of course, because nowadays we are celebrating the Medical Physics Week. So happy Medical Physics Week for all the physicists. Thank you so much.
Thank you, Dr. Ibrahim, and I will let Dr. Mai now to take the discussions and to give the question if there is and the answers. Thank you. Dr. Mai, تفضل.
Thank you, Dr. Gaber.
Dr. Mai, did you hear me?
Yes, I unmuted the audio, sorry. Thank you very much, Dr. Ibrahim, for this highly informative and insightful presentation. We truly appreciate the time and effort you have dedicated to sharing your information with us, and it was such an excellent start for our series. I think still no current questions in the chat box and nor in the Q&A. So if anyone wants to ask orally, please raise your hand and we will open the mic for you. Any questions from the audience?
I think, of course, this is a basic one, so
Okay.
I believe we will not find any inquiries, but I'm happy to hear from anyone.
Yeah, Dr. I think Abdelhamid. I think Dr. Abdelhamid. Please unmute his mic, Mr. محمد. أستاذ محمد معوض ممكن تفتح المايك لدكتور عبد الحميد. أستاذ محمد.
ايوه اتفتحوا. مساء الخير.
مساء النور، زي حضرتك يا فندم؟
الحمد لله. اولا رغم ان الموضوع بيسك ودراي تو physicians, but I like to say that the speaker really simplified the issue. The slides are very clear and his presentation is very, very simplified, although it's informative. So I appreciate it and I thank him.
Thank you, Dr.
I have a question.
Please.
You mentioned the pinhole as well as the converging collimator. And I'm happy you mentioned this because the pinhole is essential in some situations, particularly the thyroid scan.
Of course.
And my question is why we are limited in Egypt in using the pinhole, although it's not really expensive to get a pinhole collimator, whether for a small single head camera or a dual head that you can use one head with the pinhole collimator.
Okay, I think I mentioned that during my presentation because now you are asking about one single head, so it's a matter of studying our needs. So for if we are going to install this camera in one private center, he will not use it, for example, for sure, because it is not economical for him, which means it's not if the collimator is so cheap, he will also will not acquire it because it will not help him during the daily acquisitions. So let's consider he's a private center having a lot of patients, and we have only 4 to 5 patients thyroid scan. It will take time to change this collimator, and it is, by the way, it's so critical in changing it. I remember we have acquired this pinhole collimator with a Vertex gamma camera, sorry, EDAC gamma camera in 1998. And it was settled in the box, and we didn't use it since it is acquired. Because of what? Because it is not applicable to be installed on this type of gamma camera. How it comes, I don't know. So for private centers, it is not accepted because it will delay their imaging process or their patient flow. But for research center, it's okay. For governmental centers, it's okay. But you will dedicate one camera for thyroid to preserve time. I think this is my answer for your question.
Any other comment on this? Because I have a different view, because with managing the schedule, we can use a camera in certain days or day for a group of thyroid scans without changing the colorimeter every time a scattered patient comes and need to change the colorimeter. However, having heard that and having said that, it's against any rule to depend on planar imaging for thyroid scan. So I think this issue need to be studied, and nothing is for free.
Of course.
When we use the proper technique, we are getting meaningful results and meaningful outcome. Otherwise, we may hurt the patient. And I thank you for your patience.
Thank you. Thank you, Dr. Abdi.
Thank you.
I have a question, Dr. Ibrahim, if you allow me.
Yeah, please.
I want to know the main differences between the analog and digital detectors and how it will impact the clinical image.
Analog, we don't have now any analog gamma cameras. I
Okay.
think if you go to, I don't remember if it is there up till now or not in the Qasr Al Aini Center for Nuclear Medicine and Oncology. We used to have a very old one, and it have been managed by the IEA experts in order to change it into a digital one, because most of the softwares or acquisition software was obsolete and it can be used. So they get their own system and they try to digitize the images from this analog gamma camera into a digital gamma camera. But analog, no way. You will not find it here. You will not find it now. Since I was in Egypt, it was not there. It's vanished.
Okay. Thank you, Dr. Gaber.
نعم.
أختم ولا حضرتك؟
لو ما فيش أسئلة تانية نختم. أنت
كده
تختمي
خلاص.
طبعا.
No more. Okay, no more questions. Thank you very much, Dr. Ibrahim, for your valuable
Thank you so
answers
much. Thank
and
you so much.
for making today's session so engaging. Thank you, everyone who joined us this evening, for your participation and interest. We look forward to seeing you again in our upcoming sessions of the webinar series. Thank you very much and have a great evening.
Thank you so much. Thank you.
شكرا.
شكرا جزيلا.
مع
شكرا.
سلامة الله.
سلامات. مع السلامة.